Right, so in the previous video, as we relaxed one of our assumptions for linear model, right? That linear models, the models are additive. In this one, we said we are going to relax the second assumption, which says, which is basically linear. We are dealing with linear models. The truth is sometimes the true relationship between the response and the variables may be non-linear. So how do we introduce that? We introduce, okay, let me write here, non-linear relationships. Because linear relationships, they say the change is constant no matter the value. So what that basically means is for our TV advertising, whether we change our TV advertising from 51,000 to 52,000, this is a change of what? Of 1,000 Rand. It means the sales, the change in sales will be the same as someone who increased their TV advertising budget from 1,000 to 2,000, which is also a change in 1,000. If we change our TV budget by the same amount, the change in sales is the same. This is going to be, I think in real life it's going to be false. There is no way this will work, right? This budget here, there's no way that will work. So we might need to include non-linear terms. That would take care of the part of, depending on the amount, on the amount that you have already put into TV, it's also going to affect the change in sales. For someone who has a 1,000 Rand budget, the sales might not be as affected as someone who has a 51,000 budget. Or someone who has a 51,000 budget, the sales might not change as much as someone who did from 1,000 to 2,000. Makes sense? If you had no budget at all, or zero, and you put some 1,000 into advertising, the sales there would expect the sales to have a major change, because maybe with zero budget, you actually had no sales at all. So the changes there will just take into account how much a budget is there already, right? So let's look at another example. A very good example to illustrate this is very the auto data for automobiles and stuff like that is very well known in the realm of data science. The auto data, that's where many people usually start off, including the iris data set and all of those things. So this auto data is basically giving you a way to predict the miles per gallon that a car travels based on the car's horsepower, right? Based on the car's horsepower. So if we plot the data, it's going to come out like something like this. If we plot horsepower with miles per gallon on the y-axis, what is going to come out? It's going to come out like this, something like this. You can get the data set and just plot it. You see, it's going to have some shape like that, right? With the previous assumption that we had, that the change is linear, what we would have done is we would have created a line like this. If we're going to plot it, would have gone and then created a straight line model. It was going to be something like this, right? That is when we have the assumption that the change is linear. Would have had a linear model like that, straight line, simple, right? But then when we look at the graph, just looking at the graph here, those dots, you can tell that there is a curve involved there. There is a curve involved. And the curve does not come from linear assumptions. They come from non-linear assumptions. We can see there's a non-linear relationship between MPG and horsepower. A simple way to include non-linear associations or non-linear relationships in a linear model is to transform it a bit and add some predictors in the model, right? The easiest is to use what is called polynomial regression. We're going to see it later in a later chapter where we do polynomial regression. But for now, the simplest is for us to use polynomial regression. The linear model, what the linear model is saying is y is equal to beta naught, not y, let's use the correct, MPG is equal to beta naught plus beta 1 horsepower times horsepower, right? Times horsepower. But we're saying this cannot happen because looking at the shape, there must be some nonlinear terms that give rise to a curve. So we are saying there's going to be something like a curve there. So what we can do is to fit a model that gives a curve like that. That's what we can do. And this model here is nonlinear terms. And how do we create such a model? We can write it as MPG is equal to beta naught plus beta 1 times horsepower, cool, which is the linear part. The nonlinear part now comes when we add as an additional variable, which is beta 2 times horsepower squared. Horsepower squared, the polynomial part, polynomial regression. That's what we're doing now, right? Polynomial regression. We've added a horsepower squared part there. So this horsepower squared is the one that creates the curve there. The one that creates the curve there. And if you want, you can now see an increase in 1,000 rand, or let's just say 1,000 power. 1,000 joules of power. Not power. That's 1,000 joules is not power. Joule per second, that is power, right? Watts. 1,000 watts. An increase in, I don't know if horsepower in a car is horsepower measured in watts. I'm not quite sure, but whatever it's measured in that data set, whatever it's measured in that data set, if we increase it by 1,000 rand, 1,000 units, this is going to also increase this nonlinear term by 1,000 squared. So which means your change is not going to be the same throughout. It's not going to be the same throughout because of this squared term here. It's not going to be the same throughout because of that squared term there. So now what happens is this equation predicts the MPG using nonlinear function of horsepower. But it is still linear. That's why it falls under this topic. It's still a linear model. Why is it still a linear model? Because this horsepower squared, we can always break it down into B2 times we can always represent this horsepower squared as x2, as a variable called x2, and our horsepower to the power 1 by x1. So it becomes B1 MPG is equal to B naught B1 times x1 representing our horsepower, and then B2 times x2 representing our horsepower squared. So in our data set, we could have squared horsepower and then created a variable called x2. Nothing would have changed. We wouldn't know that there is this squared part. We wouldn't even know. There wouldn't be any difference. But then the difference comes when comes with the results. The results will be something curvy like this, which is the results will be okay. When you bring back the results to original formats, they'll be curvy like this. They'll take into account an even more variable data set than the linear one. You see, than the linear one. So it is still linear because we can always create dummy variables, which means that normal software that we use for simple linear regression or for multiple linear regression that is just linear can be used. It wouldn't even care that you are squaring horsepower like this. It wouldn't even care because you can always create a linear variable like that, x2. You can always create an x2 variable, and it's just a matter of squaring horsepower. Nothing has changed. If you have a 2 in horsepower, here when you say horsepower squared, it will be 4, right? You don't care that it's horsepower squared. It will just call x2. It will be x2 is 4. That's all it will do, right? So when you look at the r squared of the normal feet was equal to 0.0606, and for the nonlinear one is equal to 0.688, right? And when you look at the p-value for this horsepower squared is actually significant. So we would conclude that it is a better model than the one that doesn't have the horsepower squared, right? Someone might say, oh, okay, cool, we have included horsepower squared. What if I wanted to include horsepower cubed? Or if the person wanted to include let's say horsepower cubed, horsepower 4, horsepower to the power 5. What will happen is the curve that you'll be drawing will now be something like this. something like that, right? And this curve here, yeah, it's fine. You can do that, but it will start becoming too wiggly. It will start becoming too wiggly and results in a situation that we hate called overfitting. So you have to decide where to cut off. Are you going to do horsepower squared cubed to the power 4, 5? Whatever you're going to do, just look at how your R squared is changing and how your P values are changing, because maybe the P value for the H5 stops being significant, so you'd rather do the H4, right? So yeah, you can, but just be careful of not overfitting your data. So we've come to very close to the end of linear regression, right? We're just going to do the last section, and the last section is going to be composed of, I think, maybe 6 videos, the last 6 videos. And these videos are going to discuss, and I hope they're going to be very short videos. They're going to discuss some problems we are going to run into, or you will potentially run into when you are doing linear regression models. So stay tuned for those, because they are going to highlight some things that you need to just watch out for.